So our next speaker this morning is Caudrelier, and he's going to speak about Lagrangian multiforms and action principle for integrability.
Thank you, Elijah, and thank you so much to the organizers for giving me the opportunity to speak here. First time in the IDD conference and first time in Nordita, so this is great. So I suppose that before Benoit's talk yesterday, probably none of you had heard about Lagrangian multiforms. So what this talk is about is just give you an overview of this activity and really put it in context. What was the initial motivation, what we've done, and where we're hoping to take it further in the future. So as such, I should thank many collaborators over the years. Frank Meyerhoff, which was actually the initial person to propose this idea, and then a bunch of PhD students and postdocs and collaborators. And Benoit is the latest victim to fall for on this idea, as well as Derek Harland in Leeds. Managed to convince them there was something interesting there. So the plan, so the general context, some notions of integrability, and then Lagrangian multiforms as one of them to try and balance the landscape. And then I will tell you a bit more how it works. Essentially, for finite dimensional integrable systems, for simplicity, because this is an overview talk and it's quite short. I also apologize that things might not be super precise or detailed, but you can always ask me more later on. Some perspectives, some of which will be about extension to field theories, which some of them we know what to do, for others we don't yet, and then conclusions. So because there's going to be Lagrangians and Lax matrices, both with L, so the curly L is for Lagrangian stuff, and the straight L is for Lax stuff, and everything will be cast on in this talk. No question. So we've got these two masters that hopefully everyone knows, Lagrange and Hamilton. So probably the fact that these two formalisms are still existing today is a signal that they're very important, fundamental, and they both have pros and cons, and probably they work better when you use them interchangeably. That's the general situation, but I'd like to argue that when it comes to integrable systems, actually the situation is a bit more imbalanced. And the Hamiltonian picture in particular has been quite predominant in a certain way. And as an academic, I was quite seduced by the idea and the question to say, well, okay, so these two formalisms are really basic and well known, but when it comes to integrability, there's a bit of a favored direction. So can we restore the balance and have a notion of integrability that's purely variational? So that's really the general motivation, quite academic, but along the way we made some, I hope, what I found interesting observations. So to review, you all know that, but of course it's just a step notation. So in the Hamilton picture, you have phase space, some coordinates, let's say canonical. The dynamics is induced by Hamiltonian with Hamilton's equations. Equivalently, if you have a Poisson bracket, you can formulate things a bit more geometrically. At the other end, well, not the other end, but the other side of the story is Lagrangian formalism. There you only work with coordinates. Instead of cotangent bundle, you have a tangent bundle, and the Hamiltonian is replaced by a Lagrangian function. And the dynamics is described by the earlier Lagrange equations. The added bonus here is that they derive from a fundamental principle, the list action principle. So give yourself this action, apply the variational principle, action principle, or Hamilton principle, funnily enough, and then you get these equations of motions. And as a remark, actually, the Hamilton equations themselves are variational, and perhaps sometimes that's a bit less known, but it will be important for me later on. What you do is you work with this action instead, formulated in phase space, and if you minimize it along with the same rules as you would do normally, then you get Hamilton's equations as the earlier Lagrange equations. That observation will be quite important later on for my purposes. So as I said, there's no integrability so far. And that's where things start to be a bit imbalanced. So there's obviously historically the Hamiltonian definition of integrability It goes back to Liouville, and that we were reviewed quickly yesterday. So you have Liouville integrability if you're able to find n functionally independent functions on the phase space which Poisson commute, and being half the dimension of your phase space, so the number of degrees of freedom. So that's a really flash course on integrability. But one very important consequence that is one of the main ideas that's captured variationally in Lagrangian multiforms is the notion of hierarchy. So instead of thinking of a Hamiltonian system in isolation, when you have all these other Poisson commuting quantities, it's actually very, very fruitful to put them all on equal footing and associate a flow to each of them. By lack of a better name, you call the corresponding variable also a time variable, even though physically it's not necessarily time. But the idea is that instead of considering one system in isolation, you consider simultaneously a bunch of Hamilton equations where each flow is dictated by each of these Poisson commuting Hamiltonians. So now you've got this index k that labels the various times, and the consistency of this set of equations is ensured by the Poisson invertibility, which means that at least locally you can always find solutions that depend on all times simultaneously. So for short, I will say that they depend on a multi-time variable. And also more geometrically, what this means is that, well, it doesn't matter if you first evolve along T1 or T2 and then T3 and then along the other directions, you end up at the same point. So you have a path independence in multi-time in this picture. And that's the key idea that we're going to plug into the variational formulation, this path independence. That will be the key new ingredient to formulate a variational criterion of integrability. So before I do that, there's another well-accepted definition of integrability that we've heard a lot about already in this conference, like spare integrability. So there, the definition is quite different a priori. So you're going to say that the dynamical system is Lax integrable if you can put it in a very special form. So for finite dimensional system, usually it's written as the original Lax form with a pair LM. If you're more interested in 2D field theories, very, very roughly, you just think of L as being this partial connection. Then you get your zero curvature equation. But the key idea is that you can also extend this to a hierarchy of compatible Lax equations. We have a similar idea that you have now these various flows imposed simultaneously on some object L, the Lax matrix, and what drives the flows is various Lax matrices M. And the translation of being compatible in this language is that you have these zero curvature conditions on all these M's. Right, so, yes.
So, traditionally I think of foliating my phase space with level surfaces of these charges.
Yes.
And my real time moves my particle around one of these level surfaces.
Yes.
Is there a view like that with the multi-time?
Yeah, so you would move so
across different surfaces, or you restrict to a particular
anything.
leaf or something?
So what happens with the multi-time is that they correspond to the Hamiltonians in involution. So what you have in mind is the torus, the tori that are fixed by fixing, and then each time is going to make you go around a certain direction on this tori. That makes sense. I mean, it's higher dimensional pictures. It's not always tricky, but that would be the idea. Yeah. So there was a fundamental breakthrough that in the early days, already back to Zaharov, one of the first things they did was to try and find the Hamiltonian interpretation of something that was formulated with the Lax language. And so things developed, and there was really a strong unification idea via the idea of classical R matrix. It started with people like Sklyanin and then formalized by Semyon-Transiansky, Riemann, Drefeld, and many, many, many others. I apologize. You're close to someone I should have cited. But in short, and I will tell you more about that soon, the Lax formulation is Hamiltonian if you use a nice bracket, and now some brackets, and there will be a bit more of this below. So there's a really strong connection between these two pictures. So what about the Lagrangian criteria for integrability? That's missing. So that's where the idea of Lagrangian multiforms was originally proposed back in 2009. Originally, it was done in discrete integrable systems, but today I'm going to present what we know in the continuous setup, mainly for finite dimensional systems, because it's a bit easier, but I will tell you that what we know at the end about 2D field theories. So the general idea is that you need first to generalize your what object you work with to incorporate this idea of having a collection of flows. So that's step one. What's the object you want to minimize? And then what's the appropriate variational principle for that object? So the two steps are here. And how do you do that? So again, instead of having your traditional action with a single Lagrangian and single time, you now imagine that you have a collection of Lagrangians organized in a one form. Because it's in the multispace, because it's a one form in multispace, you can only integrate it along a one-dimensional curve here, gamma. And the essential new aspect is now yet you have an action that not only depends on the field configurations or the position configurations, but also is going to depend on the path. So if you like, the time variables also become field by themselves, and the path independence that I emphasized when we talked about having Hamiltonian evolutions is going to be part of the action principle that we're going to postulate now. So that's the new object. Yes?
This being a one form is a special case, right?
Yeah, so that's because I'm talking about finite dimensional systems. If you do field theory, 2D field theories, you would have a two form. I'll touch upon that at the end, hopefully. So what's the new variational principle now, where it comes into steps originally? There have been some better understanding more recently, but let me just capture the idea now. So what you do is that you would impose your standard action principle as you would do with respect to the coordinates q, but with the extra condition that it should now hold for any possible curve in multi-time that you can imagine. So that already brings a lot of new equations in your system. And then there's a second aspect. So when you're on solutions of the equations that you obtain here, you're going to impose that the action is stationary with respect to variation in the multipath, in the multi-time variation of the path. And that also, this one is super important, and you'll see why in a minute. So first step, the first part of the principle gives you standard Lagrange equations for each of the Lagrangian coefficients as you would expect, but now, and that would be just boring and useless if you only did that, because you would just be putting together a collection of theories that have nothing to do with each other. So the first step towards capturing integrability and compatibility is actually captured here. So now we require that the Lagrangian corresponding to time k, if you take partial derivative with respect to the velocity to another direction, that should be 0, unless you've got a j equals k. In that case, it should be something, and the something usually is the conjugate momentum in the traditional language. But here, with the added condition that it should be the same momentum for all times. So that's a very strong constraint. It's a constraint, the main message that is a constraint on the Lagrangian themselves. So that's where you start picking particular theories as opposed to putting together a collection of things that, will not be integrable in general. The second step, so now there's a bit more geometric, but when you translate what it means, you've got what we call the closure relation. So it's really just saying that on shell, this one form is closed, which you can write in components. And this one is very important because this is really direct analog of having Hamiltonians in information. So if I make a summary of what we have, what I would like to, if I organize the equations that the general principles tell you in terms of what they do, you've got something that constrains the possible Lagrangians. So that gives you a criterion for integrability. And now assuming you find candidates, or assuming you can solve these equations for the Lagrangians, you plug in there, and then you'll have your integrable equations in the Lagrange form. Yes?
just clarify, maybe you already said this compatibility condition comes from demanding path independence for gamma, is that correct?
This one, yes.
Yeah.
This one, yes, and this one is sorry. No, the independence on gamma is this one is a closure. This one comes from implying your usual action principle, but for any possible gamma.
I see.
Yeah. Yeah, it takes a bit of time to know what's going on, but
Thanks.
yeah. So why is it a good criterion for integrability? So in short, you can show that the closure relation is the direct analog of the Poisson relativity of your Hamiltonian. So it's a good indicator that we're on the good track. So in principle, this, and that's something that Franck is very keen on, but I'm not going to touch that because I find it a bit scary. In principle, that's a new angle to classify. You know, you can try and classify integrable theories with this variational principle. I'm not going to do that today. Today, much more modest, I want to answer this, complete this diagram. So the bottom line, I explained this is well understood. So you have the Hamiltonian picture of a hierarchy. You've got the lax picture of an integrable hierarchy, and you can link the two via the R matrix. And what I want to do is want to find a way to find a one form that produces these two aspects as its variational equations. So there's an almost trivial observation, and that's where the phase-space Lagrangians come into the game, is that if I'm right, or if I look for my Lagrangian coefficients in this form, PD2 minus some functions, which I call H, of course, and it so happens that you know that they Poisson commute, then actually the criteria are automatically satisfied. So you're like, oh, okay, well, okay, there's nothing to do there. Well, there's a catch. The catch is that if I plug something like that in my Lagrange equation, first of all, I don't necessarily get something in lax form. So in other words, how do you pick the kinetic part here and the Hamiltonians in such a way that your earlier Lagrange equations do take the lax form? In other words, how do you show that the lax equations are variational themselves? So that's kind of an inverse problem. You want to try, you know, the phase space of a Lagrange, of a lax formulation, and you want to do a sort of inverse Legendre transform to find the correct kinetic part, if I put it in really plain terms. And that's where this machinery comes into play. So it's called the dialgebra machinery. And we'll just check some time.
Good. So you are 17 minutes in.
Great. So some of you might know bialgebra machinery, if you know about quantum groups. So it's not a typo, bialgebra. There's a strong connection between the two, but there's also a big distinction. So the overlap is when the R matrix I'm going to talk about is Q-symmetric, very, very superficially. And also in the sense this is a dual picture. So the bialgebra business, usually what you do is you put a Lie bracket on the dual of the Lie algebra. Here I'm going to put two brackets on the same underlying vector space. So it's sort of a dual picture. But I prefer this, it's more flexible for what I want to do, especially because it allows you to do non-symmetric cases as well. So anyway, some data. So you get yourself you take a Lie algebra G, your favorite Lie algebra, 5-dimensional. And if you have at your disposal such an object capital R, so that's not a quantum R matrix, that's just to distinguish it for the small r that maybe you're more familiar with. It's still another classical object that satisfies this modified classical master equation. What happens is that this ensures that this new bracket satisfies the Jacobi identity, so you have a second Lie bracket on T. As soon as you have a Lie bracket on a Lie algebra, you can equip it with a Lie Poisson bracket. So there's an abstract definition here, but it may be in terms that are more familiar to some of you. This is just saying that you have the classical Yang-Baxter equation, and then you have a linear Sklenin-Lie bracket, if you translate. Okay. So what I do is I equip the underlying vector space with the second Lie bracket, and I denote the corresponding Lie algebra with G star bar. And what's going to be very important for us is that there is an associated lead group. And the multiplication of this lead group is a key component. So then you identify G with G star using some bilinear form, say the trace, and then there's a theorem, similar to Jensen's theorem, which gives you what are the good functions you can use for your Hamiltonians. Essentially, they're trace of powers, as you know, but anything that's invariant under the adjoint action will automatically Poisson commute with respect to that R bracket. So you get that for free with this construction. And the bonus is if you compute the corresponding Hamiltonian equations, miraculously, they take the Lax form, and NK is completely determined in terms of the Hamiltonian and the R matrix. So all these ingredients, they do the hard work for you, and I'm just going to take that and put it in my Lagrangians. So the main contribution or the main observation was, okay, what kinetic term do I write in my Lagrangian to make everything work? And that was the last observation. So if you parameterize a Lax matrix of interest or your faces of interest in this way, so it looks a bit daunting at first, but think of it as just the adjoint action, but using the multiplications twisted by this R matrix. Think of it, roughly speaking, in this way, which means that you put all your degrees of freedom in the group valued field. More precisely, it's actually a coset space because you have redundancy by the stabilizer of this fixed object that you choose. That's a fixed object, no degrees of freedom there. And then with these ingredients, the proposed formula is that thing there. So you've got the pairing, you've got the fixed object, and you've got the dynamical degrees of freedom. You've got this multiplication R here, which plays a role. The Hamiltonians are just a trace of L to the K that you take. And that's the PDQ I was after, but written now in a very, very convenient form. My purpose is because now if you vary this with this Lagrangian, what you can show is that your Lagrange equations take the form you wanted. And there's also a natural interpretation in terms of Hamiltonian because that was already done by Semmelweis. So the triangle of my diagram now is completed. Okay, so that's done. And okay, so I'm gonna, I'm doing very badly for time. Just to show you that this abstract setup at the end of the day is very concrete. You can do every possible model you can think of, but at the end of the day, it's just fixing various matrices and doing calculations. So you can do, for instance, something called the open Turner chain. You choose this matrix as your lambda, you parameterize the group in a certain way, you choose your Hamiltonians, like I said, up to a normalization, and then you just count the wheel and you get your Lagrangians. You compute the Lagrange equations for this, and you say, okay, I've reproduced Toda in a Toda hierarchy in a completely variational way. But the thing is that because everything is general, any hierarchy you can think of that falls within the diagonal setup, now you have a Lagrangian multiform for it because the details don't depend on the specific model as long as you have an R matrix. So that's the takeaway message. Choose a Lie algebra, construct an R matrix, and then you've got a multiform with this generic form. So we play this game in other contexts. So for instance, with Benoit and Anoop, a student of mine, now we say, okay, choose a Lie algebra to be some loop algebras, and then you can fall in the realm of Godin models, the rational Godin model in the cyclotomic version. And you can extend these ideas in various ways. So let me skip that, although it's fun, but perhaps it's more important to mention two-dimensional ultralocal field theory. So roughly speaking, seeing everything, a lot of things under the carpet, the ingredient is you also use loop algebras as the underlying algebraic object. You use skew-symmetric R matrices, so solutions of the classical Newton-Maxwell equation, and essentially we have a formula for this object, this Lagrangian L, that reproduces now an infinite hierarchy of zero curvature equations. Now, the key difference is that you have to work with something called two forms, and these coefficients are what's packaged in L here. And if you use this technology, so first of all, you can cover any ultralocal field theory that comes with a meromorphic Lax matrix. It has a skew symmetric R matrices, so I mean it's really a lot of them. And you can play an interesting game of coupling hierarchies together. So, for instance, we did the Rashbaliyev-Rashtikin ultralocal version of the principal current model, and you can couple it with something you wouldn't expect. The algorithm is called neural Segur, which is something that contains the nonlinear Schrödinger equation, and then you get hierarchy that contains these two equations coupled in a certain way. You can do a trigonometric version of that, which couples the anisotropic version of this PCM with the sine Gordon equation, for instance. But that's, I mean, that was just offered. So yeah, extension of these ideas that was Benoit's talk yesterday. So you can extend these ideas to the homomorphic topological theories, and at least in 3D. 4D we don't know yet. Conclusions. So yeah, it's a long-term program, started some time ago, but basically the idea was to find a variational criterion to integrability. So now we understand that, and then we showed how to apply it in finite dimension, 2D, and there's even an example in 2+1, so the concept of exactly hierarchy. Although it's motivated by integrability, it's not restricted to it. So something I skipped, but actually you can put together symmetry algebras, Lie symmetry algebras with your favorite system, and you still have a multiform for that. So it goes well beyond integrability, although it was motivated by that originally. And I'll finish, so you can read the open questions, many of them, classical level, and the big one, path integral quantization using this technology. So the idea is that because you've built in integrability directly in the action, can you do better or more, or at least recover known results from the quantum inverse scattering method using path integral quantization methods built on this object? Sorry.
Any more questions?
I just have a quick one. So just regarding the last path integral quantization point, I guess normally if you're just going back to the 1D setup, the path integrals are reasonably well defined for 1D quantum mechanics.
Yeah.
But here now you're sort of making this a multi-dimensional space. Do you have any kind of comments on the definedness of?
Yeah, so yeah, the thing, so if you think about path integral measures, so yeah, usually it's only taking into account a measure on the possible path in the positions. But now you have to incorporate the path itself in multi-time as an independent, a dependent variable. So the measure would capture that. So we think that more recently, I didn't mention that, but with Derek, we have a reformulation of this operational principle that puts actually, let's say in that language, Q and P, so the phase space variables and the times on equal footing, so that then the measure of the path integral could be defined as by viewing this as just fields of some other copy of multi-time. And so it's very speculative at the moment, but that's the first steps. Is how do you first define the multiple version of path integral? Then you can asking questions by computing things. Yeah.
Comment. Maybe another direction instead of path integral quantization, just relating to geometric quantization.
Yes,
might be more attractive.
absolutely. Especially there's a lot of quadrant orbits that we use. Yes, I agree. Yeah. I'm hoping that this would be something that can help us. So, yeah, okay.
Yeah, just wondering, and maybe it's related, but we also have a reformulation for the spectral curve and its whole story.
Yeah, so we were wondering about that. I think, I don't know if I understood your question correctly. With Benoit, so this potential term that we have in the Lagrangian that involves the various Hamiltonians in that language. There's at least in the field theory setup, we had a formalism that put us all the Lagrangian coefficients in a generating form. And then we were thinking that the infinite dimension, the correct analog of that would be to use the spectral curve as the generating function for the Hamiltonians and have a generating form. So yeah, I think we never wrote it down fully, but I think it would be probably powerful to do that, because then maybe you can bring tools from the spectral curve technology into this picture, which is already quite geometric. So yeah.
Nice.
But it's all speculative. So yeah, there's like you have these new gadgets. What can you do with it? Yes.
Yeah, so maybe I have like kind of an abstract question. So here you said that you have this closure condition for the multi-form Lagrangian, and that would imply the path independence.
Yes.
Right. So because the way I understand like this multi-form formalism is that you have like different Hamiltonians that generate like one-dimensional flows.
Yes.
Right.
Yes.
Different one-dimensional flows.
Yes.
I'm just wondering, like, can you use the multi-form formalism to define like homogeneous between these one-dimensional flows?
I don't know if it's related, it's a good point, but what we managed to do is to generalize that to flows that no longer commute, but close on a Lie algebra. So I don't know. The short answer is I don't know, but yeah, that's
I'm just saying, like,
yes, yes,
just
yes.
away from the Constantin law stuff, away from the culture or this stuff, just generally speaking, the formalism.
Yeah.
Maybe there's some kind of derived geometry happening that you can witness the homogeneity.
I think I might just grasp your question, but I didn't think of that. I cannot comment further.
Okay.
I think we should leave it here.
Yes.
Thank you very much.